Imagine cooling atoms to a temperature so close to absolute zero that they stop behaving like individual particles and merge into a single quantum entity. This isn't science fiction. Carl-Wieman made it happen, transforming one of physics' most abstract predictions into observable reality. Carl-Wieman is a Nobel Prize-winning physicist whose work bridged the gap between theoretical quantum mechanics and experimental proof. For decades, quantum physics existed primarily in mathematical equations and thought experiments, describing a bizarre microscopic world that seemed impossible to witness directly. Wieman changed that. The challenge he tackled centered on a peculiar prediction made by Albert Einstein and Satyendranath Bose in the 1920s. They theorized that at temperatures approaching absolute zero, atoms would lose their individual identities and condense into a single quantum state, behaving as one unified wave rather than separate particles. This phenomenon, called a Bose-Einstein condensate, represented a new state of matter entirely distinct from solids, liquids, gases, or plasmas. For 70 years, this remained purely theoretical. The technical obstacles were staggering. Atoms needed to be cooled to within a few billionths of a degree above absolute zero, the coldest temperature possible in the universe. At room temperature, atoms zip around at hundreds of meters per second. Wieman and his team needed to slow them to a near standstill. In 1995, Wieman and his colleague Eric Cornell achieved the impossible at the University of Colorado Boulder. Using lasers and magnetic fields, they trapped and cooled rubidium atoms to 200 billionths of a degree above absolute zero. At that moment, roughly 2,000 atoms suddenly merged into a single quantum entity, creating the first Bose-Einstein condensate ever observed. The achievement was more than a confirmation of theory. It opened a window into quantum behavior at a scale large enough to observe and manipulate. In the quantum world, particles exist in multiple states simultaneously, tunnel through barriers, and become entangled across distances. These effects usually vanish at larger scales, but the condensate allowed scientists to see quantum mechanics operating in a visible cloud of atoms. The applications extended far beyond pure physics. Bose-Einstein condensates became tools for developing atomic clocks of unprecedented precision, essential for GPS technology and fundamental physics research. They enabled advances in quantum computing, where information is processed using quantum states rather than traditional bits. Scientists used them to simulate complex quantum systems, testing theories about everything from superconductivity to the behavior of neutron stars. Wieman's impact reached beyond the laboratory. Recognizing that physics education often failed to convey the excitement and logic of the discipline, he turned his attention to teaching methods. He applied the same rigorous experimental approach to education that he had used in physics, testing different teaching techniques and measuring their effectiveness. His research revealed that traditional lecture-based instruction was far less effective than active learning approaches. Students learn more when they grapple with concepts through problem-solving, discussion, and hands-on experimentation. These findings influenced physics education worldwide, reshaping how universities teach science. The transformation of quantum physics from abstract mathematics to tangible reality represents one of the great experimental achievements of modern science. Carl-Wieman demonstrated that the strange predictions of quantum theory weren't just mathematical curiosities, but genuine features of our universe, observable and useful. His work created new technologies, opened new fields of research, and changed how we teach the next generation of scientists. The quantum world, once hidden in equations, became something we could see, touch, and harness.